Yeah, if I increase my largest dt here, and that could potentially, right? So because you can see this is probably the location where you are dramatically decreasing your delta t, right? So I have pretty large delta t and I have to decrease it, then I have to decrease it rapidly, right? To kind of start to resolve this sudden jump. Right, so if my delta t initially, this is probably my largest value, right? So if my largest value is even larger than that, then I have to decrease it more dramatically over this region. All right. So if you want a more advanced solver, then not only would the loop be assessing the convergence, it would also be assessing the accuracy of the solver. If you have two different schemes, right, you get two different next values, and you would keep cutting the delta t if the two values are different, too different by your criteria. So that leads us to a tour of what MATLAB has. So MATLAB has a bunch of ODE solvers. The most famous one is probably ODE45. So I think a good way is probably just to look at the documentation of ODE45, right? It basically takes two time integration schemes in order for it to compare the error. So if you look at the algorithm, right? It based on explicit Runge-Kutta. So we have studied the Runge-Kutta 2, a two-step Runge-Kutta. So here, the dormant Prince pair is actually a pair of Runge-Kutta schemes, 4-stage and 5-stage. It's a pair in the sense that if you want to compute the solution using both schemes, the two schemes actually reuses a lot of the computation, in the sense that it's not actually, the computation cost is actually much less than applying one scheme and applying another scheme, because they actually share a lot of computations. In that sense, you don't actually spend much more computation while having two different results, two independent results to compare against to assess the computation error, right? So that's why it's usually the default one to use. There is this lucky coincidence when you have a 4th order scheme and a 5th order scheme that has can share a lot of computation. Okay, but through using the same idea, MATLAB actually has this ODE 113. So both ODE45 and 113 uses explicit time integration methods, right? But 113 actually has a lot more schemes embedded than ODE45. It's a variable step, variable order scheme that solves, that uses a scheme all the way from order 1 to order 13. So it has a lot of more variations you can go to, right? I mean, the reason it has so many different orders is exactly because of stability constraints of explicit time integration schemes. Because sometimes your delta t is so limited by stability that even using a very low order scheme is going to give you very high accuracy, right? And in other times, your accuracy is not limited by, your delta t is not limited by stability at all. It's just limited by accuracy. And that's when it's worthwhile to use a higher order scheme. So these are MATLAB's reservoir for explicit time integration schemes. Then when you actually have a very stiff system, MATLAB also has, for example, 23S. So that's MATLAB's default stiff ODE solvers. So what this does is that it basically does what we do with backward order, but using 2nd and 3rd order schemes. Okay, and one thing to note is that whenever you consider implicit time integration And if you go to ODE set for the options, it might be a good idea to provide the Jacobian. So Jacobian is one of the things you provide with which is used by the implicit schemes. If you don't provide, MATLAB is going to compute it via finite difference. And in our case, for our backward order, we actually have implemented explicit Jacobian, right, for us to use. If we don't have it, we'll have to do finite difference, perturb you a little bit to get what the Jacobian is. All right. So that's kind of what we have with MATLAB. And for any other package, if you use Julia or use Python, right, there are similar schemes to use. The biggest distinction is usually you have an explicit time integration scheme and you have a implicit, which is suitable for solving stiff systems.